All right. Thank you, Paxton. As she said, I'm Cody Newlun. I'm from the physics department here at Hastings College. I'm currently a senior. I'm going to graduate in May. And today I'm going to talk to you about my senior project I've been doing all year, which is the study of piezoelectric transducers that were used in an effort to produce electrical energy from footsteps. So I'll give you a little overview of today, talk about my motivation behind this project, introduce you to the piezoelectric effect and a little bit about its history, talk to you about the materials and some of the applications that you probably already use piezoelectric materials, you don't even realize it, and then talk about how they're produced, and then talk about some of the tests that I performed on these piezoelectric materials, as well as how I created the Footstep Generator. And then I will talk to you about its overall performance and maybe some potential applications of that. So today's society, we're dependent on electricity. We've been dependent on electricity for a long time, and we're starting to realize that our current electricity generation techniques are maybe harmful for the environment. So renewable sources of energy are a growing topic, and there's a demand for clean, dependable, and efficient energy sources. So I thought of, when I started this project, I wanted to do something along the lines of energy, producing energy, or something like that. So I thought, what's a wasted energy that's wasted every day? And that's with our footsteps. We put out an energy, a vibration, every time we step, and we take thousands of steps per day. And there's actually a way to harvest that energy and convert that into electrical energy, and that's through piezoelectricity. And just a little bit of background, it was discovered in 1880 by the Curie brothers. They were the first to be able to produce a charge on the surface of a crystalline structure after applying a pressure to it. And a little bit about the word, it's kind of a funky word. Piezo means to squeeze, so it literally means to squeeze for electricity. So that brings me to the piezoelectric effect. There's two forms of it, the direct and converse piezoelectric effect. So the direct is the one that I'll be exhibiting, and it's when an electric charge is formed on the surface of a crystalline structure after a pressure is applied. And those are usually called generators or sensors, and I'll talk a little bit about the applications of that. And then there's the converse electric effect, and that's when the material starts to strain after a voltage is ran through the material, and those are called actuators. So as I said, you probably have already used piezoelectric materials without even knowing it. As far as like the generators, so the direct piezoelectric effect, they're used in a lot of force sensing applications. They're actually used in igniters, so like maybe on your grill or a cigarette lighter, they're actually used there. Ultrasound and sonar, they're used, pretty interesting, they're used to actually create sound waves and to detect sound waves. And then as well as musical instrument, they're used to amplify signals as well. As far as the converse electric effects, so the actuators, they're used for small electronics and like speakers, inkjet printers. They're used to adjust optical equipment, like in telescopes, and as well as diesel fuel injectors. And then they're used in the process for developing microelectronics. So a little bit about the piezoelectric materials. One good thing about them is they require very little deflection in order to produce a voltage. However, they cannot produce a voltage off a static force. So you have to keep pressing on the piezoelectric materials in order to create a voltage. And just a few examples of these crystalline structures that I keep talking about: quartz, topaz, tourmaline, bone, tendon, enamel, lead, zirconate, titanate, and polyvinylidene difluoride. Say that 5 times fast. But PZT right there, that lead, zirconate, titanate, that's the material that I focused on. That's the most common, it's the cheapest, so that's what I had to use. And these two pictures here, if you can see my laser, those are the materials that I used. So the upper is a cheaper transducer, which I actually have a bunch of them if you want to look at them at the end. And that's what I used for my Footstep Generator as well as all my testing. And then this bottom one was a more expensive material that I used just to look at some characteristics of the material. So as far as the molecular structure goes, it's called a perovskite molecular structure. And what's unique about these is they have a larger cation and a smaller cation, and those create a charge separations, and those are called dipoles. And with these dipoles, it puts them into the category called ferroelectric materials, so that's a larger category that piezoelectric materials fall into. And with these dipoles, we're able to actually produce piezoelectric materials. So as you see here in this picture, the dipoles are randomly oriented, and in order to get those oriented in the way that we can produce piezoelectric materials, we need to heat the material up to a temperature called the Curie temperature, named after the Curie brothers. And what that does is that is able to reorient the dipoles with respect to an electric field that's applied to the material. So then after that's done, you cool the material here at the end here, and the dipoles are aligned with respect to the electric field, and you have a piezoelectric material. These diagrams are exhibiting the direct piezoelectric effect. So the upper two pictures here, the charges within the material are balanced. They have what's called a dipole moment vectors, and those cancel each other out, so there's no charges sitting on the surface of the material. And then when a pressure is applied here, the charges become unbalanced, and that's what causes positive and negative charges to go to opposite sides of the surface of the material, and you're creating a voltage. And we're able to collect those charges and use that for electricity. So I keep saying transducers. That's a device that can convert energy from one form to another. So in this case, we're converting kinetic energy, so the energy we get from motion, to electrical energy. They produce an AC voltage, meaning that it oscillates from a positive voltage to a negative voltage. And how it does that is when you press down on the material, it creates a positive voltage, and when you release, it creates a negative voltage. So in order to charge a battery or power like LED lights, which is what I was looking to do, you need to have a DC voltage where it's all positive. So in order to do that, I use it's called a full wave bridge rectifier, and that's able to convert AC to DC, and these are the pictures here. So this is the guy I used here, and then this is the schematic of that. So these are voltage time plots. Up here at the top is a voltage time plot of the voltage produced off the piezoelectric transducer after the rectifier, or before the rectifier, excuse me. And I labeled here, so this positive voltage is me pushing on the material, and this is me releasing from the material. So you can see the positive and negative. And then down here below is after it has gone through the rectifier, it produces all positive voltage, which we are able to use that for charging a battery or powering LEDs. So a little bit about the transducer. It came from a DigiKey manufacturers. This transducer actually displays both piezoelectric effects, so I actually am able to run current through this, and it can create a high-pitched sound. But I use it for the direct piezoelectric effect, so hitting it would produce a voltage. They're 1.3 inches in diameter, and again, as I said, they're the PZT material, and you can see roughly the size of these materials down there. And as you can see here in this picture, the negative and positive leads, that's what's connecting those charges that I was talking about after the material is struck. So I decided to do a couple of tests with these piezoelectric materials. The first test was to see how different forces produce different voltages. And ideally, I'd want it to be linear. You know, the higher the force would be the higher the voltage produced, thus the higher power. So I used the Logger Pro program, and I manually struck the transducer with a metal rod, and using a force plate, I was able to measure the force, and I was able to measure the voltage across a 10 kilo ohm resistor. And as you can see in this next slide, it's very inconsistent. What I got from this was down here in the bottom, this is force, and anything greater than 300 I saw was very inconsistent. So if you look here, you get kind of a linear relationship, but what I got from this was I was using pretty cheap materials, so maybe if I looked at a more expensive, more well-manufactured material, I would see a better linear relationship. But overall, you can see as the force increases, I get more power out of the transducer. Another thing I did was test the frequency. I did a range from 5 to 100 hertz using this mechanical vibrator here with a wave function generator. And what this did was it just hit the transducer. So 5 hertz, I'd be hitting it 5 times a second. So I was able to measure voltage, and interestingly enough, you can see here in the middle there, around 50 hertz, it peaked with higher voltage, and then it did that again with the current. So with current and voltage, you can get power. And so you can see the peak power was around 50 hertz, but as you can see here, I'm in the milliwatt range of power. So very, very low power, but I was able to see its frequency response. So with all these tests being done and all my knowledge about the piezoelectric materials, I was able to create a footstep generator. It's a 20-inch by 24 floor tile, essentially, that is spring-loaded, has springs on all four corners there. I brought it with me. You guys can come afterwards and check it out, see what it does, make sure that I'm not performing magic or anything. And so as you can see here, I used 3-inch bolts for contacts on the transducers to create that vibration on the surface there. So as far as the piezoelectric elements went, I did a 7x7 array. So I did 7 elements in series, and what that did was it would increase the voltage across the circuit there, and then I did 7 of those rows in parallel, and that would increase the current. So that would overall increase the power produced by the footstep generator. And then we had some troubles loading this onto the computer for some reason. It worked on my computer, but not here. But anyway, this is supposed to be a little diagram here, and so I had my 7x7 array. It's supposed to go through the bridge rectifier, charge a 9-volt battery, which I was able to do, and then connect that to a switch, and then connect that to a load, in this case LEDs. So as you can see here, I have a good picture here. So full wave bridge rectifier, charging the battery with the switch, and then as you can see, I was able to power LED lights. So another thing I wanted to do is just verify that it produced energy. So I connected it to a 150 microfarad capacitor, and so I have the number of steps with the voltage produced, and I was able to pretty good linear relationship. So each step I was able to put around 200 millivolts into the capacitor. But however, if you use the energy formula for a capacitor, that E equals 1/2 CV squared, I was able, you can see here, 16 microjoules, so very, very low energy. So the overall efficiency of the transducers is pretty low. So another thing I did was just do tests with 50 steps each, just looking at the average voltage and current produced. So as you can see, around 67 volts and for an average voltage, and average current was around 39.9 microamps, so that's 10 to the negative 6 amps. So pretty low current, but high voltage. Maximum voltage around 115 and maximum current around 99, with an average power around 3 milliwatts. So overall, high voltage but low current produced low power in this case. But with the low power, that was what other people who have done recent projects like this, they were in the milliwatt range as well. So overall, the footstep generator produced what I expected. So overall, my results, as I said, force and frequency applied to the transducers can vary the production of the piezoelectric transducers. So I was able to charge a 9-volt battery and light up an LED display. And as you can see here, I actually brought it with me. So this little LED right here, I hooked it up, and I think, can you guys see that? It's flashing those LEDs for each step. You guys can try it out afterwards. And so some of my limitations for this project, as you saw there, the accuracy of the bolts on the transducer, there's 49 of those things. I don't know if they were all hitting at the same time or the same force. So that would be something to go back and look at, as well as looking at trying to get a better understanding of the behavior of the transducers. As you saw in the force testing, it was very random. So maybe look at maybe another manufacturer, another material as well. And then also I had a little bit of trouble with my precision capabilities of my measurement devices. Some of my voltmeters or ammeters didn't have a high enough sampling rate, maybe to catch that quick footstep that was being applied to the footstep generator, so that might have been a source for my error. So just some concerns with piezoelectricity. As I said, it's high voltage but low current, so that's low power. Low efficiency, we're putting in joules of energy, and we're only getting out, as I showed, microjoules of energy. So very low efficiency in that case. And then with piezoelectric elements, over time, if they're overstressed, they may lose their capabilities. I noticed that when I was doing my force testing, when I kept hitting it with the rod, I noticed over time that it was decreasing the amount of voltage produced. And as I said, when the piezoelectric materials are produced, they're heated up to a high temperature to align those dipoles. So if they're exposed to high temperatures, that may affect those dipoles and reorient those in a way to where it would decrease its capabilities. And then also, we may need a higher frequency or a higher force to produce a significant amount of power. So what's the overall scope of this? There is high foot traffic areas such as sidewalks, hallways, train stations, airports, where everybody's walking around. What if we could make a floor of this, expand the project to where we could maybe power LED lights for the hallways or for inside of the airports, and as well as gyms, dance floors, have some crazy dance revolution. I don't know. And then also there's been studies done with roadways and train tracks trying to produce electricity off of cars and trains going over the tracks, trying to collect those vibrations to produce electricity. And then another interesting thing I saw during my research was the shoe inserts. There's been studies done where they put these transducers inside of shoes, and maybe for survival or military applications, as they walk around, they could charge batteries for GPSs, small electronics, something like that. So I thought that was pretty interesting. So a few acknowledgments. I'd like to thank the Hastings College Physics Department for funding my project, my academic advisor, Dr. Steve Beaver, and as well as my buddy Mark Nellis for helping with my data collection. He was stepping on this thing a lot, so thank you for that. And I'd also like to thank Alpha Chi and Hastings College for hosting this good day. And with that, that's all I have for you, and I can open it up for any questions. Yeah. Oh gosh. Oh gosh.
In the future on electric vehicles, problems obviously with charging stations. Could you make the quality of your pads, to something where a car could generate its own power somewhat? That's the problem.
Yeah.
EVs.
Yeah. That'd be really interesting. I think the problem with piezoelectric materials is, as I showed here, they're pretty low in efficiency. So if there's material scientists out there that are trying to enhance the capabilities of the material, but as of right now, there's not. I guess there's not the materials out there that they've found that can produce significant amount of electricity to even bother, I guess, with it. But yeah, that'd be really interesting, though. So.
You connected 7 in series, and I'm wondering if not all of those bolts at the same time, would the inverse piezoelectric effect cause you to lose energy?
The inverse?
Right, because you're deforming the
Yeah.
piezoelectrics that happen in it,
Yeah, it might. Some of the resistances going through those elements might have decreased the overall efficiency, so that would be something to go back and look through. And I know I've read some papers that were talking about the impedance of the elements was not ideal, so yeah.
So I'm just kind of curious as to how easily this could be scaled up or down. So if you could say have a big grid of say 7 individual piezoelectrics. So
okay.
Instead of just one big panel going up and down, maybe you could have say when your heel hits, it pushes down on one. Then when the ball of your foot hits, it hits another one.
Yeah.
So, what do you think about that, sort of?
I guess, that's interesting. So you're saying the shoe inserts or large scale? Or
Yeah.
So, that would be something interesting to look at as far as, when your heel hits and then when your toes hit it, I guess. Yeah, so maybe you're trying to produce twice as much. Yeah, that'd be something interesting to look at. As far as this, it's spring-loaded. I'm trying to get them all to hit at the same time. But yeah, I did think about hitting them at different times, maybe to try to produce more electricity. So yeah, that'd be interesting too. So. Dr. Buck?
Would there be a way potentially for us to sell our steps?
That sounds like a question from an economics teacher. I mean, I'll sell my Footsteps if you want to buy them. But yeah, that would be interesting, yeah. So how many milliwatts of power you produce today? So yeah, that'd be really interesting.
Are you going to go any further with this? Do you plan on exploring it further?
I would like to. Finals are coming up, but I mean, I would like to. I still have a paper to finish, so maybe try to do maybe a few more tests and conclude that in my paper. But yeah, one thing that I would like to look at was looking at like the impulse response. So I hit when I did the force testing, I hit it really quick, so it would create like a pulse of voltage. And I would kind of like to look at maybe looking at different sampling rates to see was I actually collecting the maximum voltage. So that would be something interesting to look at as far as there. So yeah. Any others?